Okay, great. So in the previous video, I defined the dot product using the first definition that I've written there, which is to say that v dotted with w is the length of v times the length of w times the cosine of the angle between them, theta. Okay. I proved also that the dot product is equivalent to v dot w equal to v1w1 plus v2w2, where those are the components in the normal Euclidean orthonormal basis. Okay, we could have chosen to define our dot product using the second definition, but the first one is preferable because it's more general and it doesn't refer to any specific basis necessarily. Okay, it's basis independent. It's just referring to the length of two vectors and the angle between them. And this brings us to our main point. Okay, the reason the dot product exists in the first place, defined any which way that you choose, is because the dot product is invariant. Okay, it's an invariant quantity. Okay, the reason is this: think about what a vector is. A vector is it's a directed line segment. Okay, it has a length and a direction. Now, that green vector, no matter what coordinate system you use, everybody must agree on the length of that vector and its direction. Okay, no matter what coordinate system you're using. Okay, think about it like this: if you measure that vector using a ruler with centimeters, inches, kilometers, whether you're using an orthonormal basis or a skewed basis or even a curvilinear coordinate system, it doesn't matter. The vector is the vector is the vector. Okay, it has to be the length that it is. So every observer in any coordinate system must measure the same length and must measure the same direction. So the dot product, being defined the way it is an invariant quantity. Okay, so if you do v dotted with v, for example, you would get v1 squared plus v2 squared, which is the length of v squared. So this length, the length of that vector, is invariant. And so the dot product is invariant. And this will become very important as we move into more complicated mathematics and physics. But the point is that a vector is inherently an invariant object, and it's part of a larger class of objects called tensors, which include scalars, vectors, and higher rank, it's called tensors. These are objects which are inherently invariant under transformation of coordinate system. In fact, Lillian Lieber once called them the facts of the universe. So we will be looking into this in greater detail in the coming videos.